During the past 25 years, we have started to understand our place in the cosmos. This was a question that could not be answered by studies of the large-scale structure of the universe. It required the exploration and observations of stars in our local part of the Milky Way. The discovery of the first exoplanet orbiting a solar-type star was a pivotal moment in the history of humankind. Our next speaker is Michel Mayor. He was born in 1942 in Lausanne, Switzerland. Michel Mayor did his undergraduate studies at the University of Lausanne and his PhD in astronomy at the Geneva Observatory. He is since 1988 full professor at the University of Geneva. Please join me in welcoming Michel Mayor to the stage to tell us about the development that led to this year's Nobel Prize.
Good morning, ladies and gentlemen. I feel very quite honored to be here and to present to you a very old problem in astrophysics. Something is not working. Okay. Yes, we are not the first to discuss this kind of problem. Already more than 2,000 years ago, the Greek philosopher was discussing having a dream to have some other world, an infinite number of worlds in the universe. In the same letter of Epicurus, in the second part of this letter, he discussed the fact that maybe some of these worlds could have some living species, and maybe some others will not have. So you see this kind of, it was not focused on planets, but it was a general philosophical dream. And in fact, this dream continued all the way during the last 2 millennium. For example, you have the philosopher Albertus Magnus in the 12th and 13th century. He said this very good sentence for us. Do there exist many worlds, or there be a single world? This is one of the most noble and exalted questions in the study of the nature. And you see, for example, almost at the same period, the Bishop of Paris asked the Pope the permission to teach the question of the plurality of worlds at the Sorbonne University. And you have many other steps in this kind of discussion during the last 2 millennium. And I will jump to the last part of this list. And for example, it's only in the middle of the 20th century that the basic ideas for the formation of planets arrived. So it's a quite new moment for this theory. And for example, you have the name of Victor Safronov also, having given the step to understand the formation of planetary system. So, very old domain, but a very recent domain of physics. Very slow reaction of the computer. Why? No reaction. No reaction. Oh, yes, here. Okay, if we are moving to the more modern part of the story, most of you know that the sun is only one star among 200 billion of stars in the Milky Way. So this is evidently not our own Milky Way because we don't have the possibility to go out to take a picture, but it is a very similar galaxy. So the sun will be a very common star in the outer part of such a system. Typically, the light will need something like 100,000 years to cross the full Milky Way, so it's really huge. And you can notice maybe in some place here along the spiral arm of this galaxy, you have some spots here. It's evidently not stars, but it's a huge cloud of gas, hydrogen, and helium. And I will speak about later on this kind of spot. If we are looking with a modern telescope in the central part of our Milky Way, this is typically what we can see. So, millions of stars. So the question is not to find additional stars. The sun is a star. It's just to learn if we have some planet orbiting this one or this one, and so on. So this is a modern view of this question. Do we have other planetary systems around orbiting other stars? And maybe a second question, do we have rocky planet, terrestrial type planet, and maybe life? So it's very strange to see that it's a very common idea that, okay, everybody was convinced that we should have planetary system orbiting other stars. But it's absolutely not true. If you look in the literature, in the astronomical literature during the last century, you see that the most respectable astronomers, Jeans, Shapley, Russell, and so on, do not consider that we have any planetary system in the Milky Way, or maybe few exceptional one. And drastically, the idea changed in 1943, and for a very bad reason, in fact. But it was only in 1952 that we have the good reason why we have. This is a logarithmic scale here. So you see this is 100, this is 0, but you see that this is 10 billion. And suddenly we jump to a huge number of planetary systems in the Milky Way. And the modern measurements are exactly at this kind of level, very high level. So you see that the idea changed considerably during the last century. So going back to this big cloud we have seen on the previous picture, this is a very famous and known Orion Nebula. It's a big cloud. It's something like 100,000 times the mass of the sun. So, time to time, for some physical reason, you have a collapse of the cloud to form new generation of stars. So continuously in the Milky Way, we have new formation of stars. And as a byproduct of the formation of the star, we have the formation of planets. So we have, from about 70 years, we have a good idea to believe, good reason to believe that we have planetary system almost around every star. The question was to detect this object. For example, here you have a picture made by the Hubble Space Telescope. You see this again, the Orion Nebula here, and looking on some of these young stars. When I say young stars, is something object with an age of about few million years of age. So for you, we consider few million years is not so young, but if you compare to the age of the sun with 4 billion years, really they are young. So some of them are going out of the cloud here, and if you are looking with a high resolution of the space telescope, you can notice on the right that you have some small dark disk around the young stars. And this is disk of dust and gas fastly orbiting around the star and not having the possibility to fall down immediately on the young star. And this is the interesting part, because this is the place where you have the possibility to form new planetary systems. it was already suspected by Kant and Laplace several centuries ago. We need to have nebula to form planetary system. But up to recently, we do not have the reason to believe where this kind of disk were coming. And this is a good image of this planetary system, planetary disk. So maybe not of you are very familiar with the Doppler effect. So as it is at the root of what we did with Didier to detect the first planet, I take a few minutes, a few seconds to explain. Let's imagine you have a small animal jumping on the water. So evidently, if it's jumping on the same place, you will have some wave, circular waves going around. But if the small animal is moving, you see that evidently all the waves will be compressed in the direction of the motion and diluted on the other side. This is the Doppler effect. This is present for any kind of density phenomena. For example, density wave phenomena. You have acoustic, you know very well the sound, the change of the tonality of in the domain of acoustic. This is true on the surface of water, and it's also true in the domain of light. So this is the effect we are using to measure the change of the velocity of stars. Why? If you have a planet orbiting a star, we cannot see the planet, but what we can measure is the change of the velocity of the star. And if you see a star moving like this, you should have somebody perturbating the motion of the star. And this is the phenomena we have been using 25 years ago to detect the first planet. We cannot detect directly the planet, but we have detected the change of the velocity of the star. And here you have the luminosity with the wavelengths, and we can detect the small change of the wavelengths due to the planet. Presently, evidently, the planets are so small that the change of the velocity and change of the wavelengths are extremely small. So this was the difficulty of this kind of problem. So our first sight was a relatively old and modest telescope of 2-meter class telescope here in Haute-Provence, French Observatory. And this is the big dome here where we have this telescope. And this is a place where we have developed with some French colleagues a new instrument to precisely measure the velocity of stars. So what is new is not the telescope, it's a very old one. In fact, it's just to collect photons. In fact, what was interesting was the new spectrograph. And it was a surprise that after a very short beginning of the program we did with Didier, that we detect a strange object. Strange, why it was strange? Because the period was only 4.2 days. It was a Jupiter-type planet, but with a period as short as 4 days. And this was absolutely unexpected by the theory, because the theory predicts to form a giant planet like Jupiter, you need to agglomerate ice particles. And evidently, we do not have ice particles so close to the star. So the theory was expecting that giant planet could only have orbital period larger than 10 years. And here you have 4 days. And 4 days is a discrepancy by the theory by a factor 1,000. It was not a small effect. So this was the reason why we have decided to delay the publication, the announcement of this object by 1 season, to do additional measurement to eliminate other possibilities. What kind of possibilities? It could be if you have a rotating stars with magnetic field. So you have spots on the surface, so maybe you have an apparent change of the velocity, absolutely not related to any companion. So, and we have other possibilities. So we have decided to be slow and to remeasure to be sure of the reality of that the planetary hypothesis was the only one. Oh, no, I jump by about 20 years. So in the north of Chile, you have an altiplano at 5,000 meters of altitude, and recently, international collaboration between Europe, US, and Japan have developed a set of something like 60 dishes of 12 meters of diameter. So with all these instruments, you can look at the same time in the same direction, and then after you combine the luminosity, the waves received by the different antenna, to have a very, very sharp images of the object you are measuring. So evidently, this instrument is not working in the infrared. It's the reason why it's a high altitude. It's not devoted only to planet research, but also to understand the formation of stars, formation of galaxies, and to study the interstellar medium. A few years ago, some colleagues used this kind of instrument to observe an object. It's a small cloud. It's much smaller than the Orion Nebula, and to look in the middle of this cloud to see a young star. The name is HL Tau. And you see that around this object, you can detect an accretion disk, a disk of matter, exactly as expected from the theory, with some ring of matter, and maybe this is an image of the formation of a planetary system. And today, we have a huge excitation to use this very complex instrument to study the formation of planetary system. And this, in some sense, is this part of the explanation why we have a period as short as 4 days. Why? What is the explanation? In fact, it's very nice to see that the explanation was already ready in the literature from 1980. Two colleagues, Peter Goldreich and Scott Tremaine, published a paper discussing the theory where you have a disk of matter and you have some small object embedded inside. What is the time scale for, because the object will create some waves in this disk, and this excess of matter in some position will react. It's called Lindblad resonance. Lindblad is a Swedish astronomer. And the reaction of this wave to the motion of the object will create a migration towards the center of the system. But eventually, this was mostly devoted to the possible evolution of a small galaxy like the Magellanic Cloud embedded in the disk of our own galaxy. So probably most of our colleagues was people interested in galaxies. But in the same abstract of this paper, it was explicitly written, Jupiter was not born where it is today. So this, you see that today we have the possibility to progress in the measurement of the formation of planetary systems. Thank you. Going back to the time, with some colleagues, French colleagues, we start already doing what is called the cross-correlation technique. What is this? When you have a spectra, you have dozens of thousands of atomic absorption lines. So if you have the luminous continuum of the light in the spectra, you have a huge density forest of atomic lines. So if in the old time, people were measuring the position of one line, another one, and another one, to determine the shift, the Doppler shift, it was extremely boring, extremely inefficient. So the idea proposed by Felget in 1953 already was to try to design an instrument to concentrate all the information of the spectra to one single quantity, the velocity. And this is done by doing some kind of template. Here, you can see a template here, something like the negative of the spectra. And then after you have, by some optical device, you can do some shift relatively to the other one. When the lines are in front of the small hole, in fact, you have very small quantity of luminosity inside. If you are out of the Doppler position, you have more light. So it's a very nice trick to have immediately the velocity. And evidently, this was the first instrument designed in 1977 with a relatively moderate precision, not adapted for planets, and put on a 1 meter telescope. And this was the first instrument of a series of instruments. The second one, LOD, was used to detect the first planet. And you see that it's a big jump of precision. We jumped to 13 meters per second. And now I will not discuss all these instruments, but only the last two lines. For example, we have ARPS instrument implemented on a 3.6 meter telescope in Chile and another one in La Palma. And we have about 1 meter per second. And the last line is a quite new instrument implemented on 4 8.2 meter telescope. This is equivalent to receive the luminosity of a 16 meter telescope. But going back to ARPS, just we are looking for change of the velocity of star like this. This is the power of this kind of technique. And this was used already from something like 40 years ago. And I gave to the museum here, the Nobel Museum, the original plate. It's used already 40 years ago in Haute-Provence Observatory with this thousand of absorption lines, small hole in a coating of chromium. So these are the team having designed and developed the LOD spectrograph. And I will take the time to specifically, put some emphasis on the man top in the middle with white hair. It's André Baran. He was the chief optician, having designed the optics of this instrument. One is missing also on this slide. So then after we have the development of ARP spectrograph, eventually having succeeded to find planet with the first LOD instrument, we try to develop new instrumentation. And this is a copy of ARPS implemented almost 20 years ago at La Silla. You see the optical system. It's a vacuum tank. It's much more ambitious. I will not discuss the 4,000 planetary system detected today, but just to give some idea how it works. You have access to the telescope, you have the spectrograph, you set the telescope in direction of star, and you measure the Doppler shift. And in the diagram here, you have the date and you have the velocity. So every red point is a velocity measured. And then a day later, you repeat the measurement, another point, and so on. After 1 week, we continue. The next season, you continue, and so on. And after you see something like 2,000 days, you have this forest of red points. And you can imagine by eye that you have something like wavy like this, so you have a change of the velocity. But it's not true. You will let the computer to analyze this data, and will suggest that you have 7 planets orbiting. So if you have 1 planet orbiting a star, the star will have a motion like this. So if you have a plot like this, you will have something like this. If you have 2 planets, you will have something like this. If you have 7 planets, you have this. I will not be able to do. So, okay, this is typically, today we have the possibility to detect not only planet, but full complicated planetary system. And you can notice the period, maybe not everybody can read, but the period of this object, 1 day, 5 days, 16 days, and so on. We do not have equivalent in the solar system. And the last 20 years, we have discovered a huge diversity of planetary systems. Our own planetary system is certainly not a typical example. So, and presently we have the possibility to combine the measurement done by satellites. You're looking for transit. When you have a star, we have a planet, you have the possibility to see a small, deep, periodic dip of the luminosity. It's some kind of an eclipse here. And you have a very famous telescope right now, the Kepler telescope. And you have on the upper slide here, you have the distribution of the size in unit of Earth. So most of the objects crossing the disk of star are very small planets. And the second part below, you have the measurement we did with Doppler effect, and you see most of the objects we are discovering are low-mass planets. And evidently, for the future, we'll go back to this point, that we are interested in still smaller mass planet. So, when we combine the measurement made by this kind of spacecraft, like Kepler, with Doppler effect, we have the possibility to start to do some physics of planets and to try to see if the planets are rocky planet, gaseous planet, ocean planet, a huge diversity of systems. And this is what we start almost 20 years ago. We have detected a planetary system with a planet with a period as short as 3.5 days. So evidently, we try to detect the orbit, the transit, and we are lucky enough because the orbital plane was inclined in a good way. And in September 99, exactly at the time predicted by the velocities, we observe this small dip of the luminosity of the star. So we cannot see the planet. We are only looking for the dip of luminosity. And our colleagues repeat the measurements 1 year later with the Hubble Space Telescope, and you see the quality. When you are above the atmosphere, you have this huge quality measurement of the transit. So immediately what you say, what you dream, if the quality is so huge, we have a chance to detect very small planet. Because Jupiter has a size about 10 times smaller than the Sun, so the dip will be 1/10 times 1 time, so 1% of the luminosity. But if it is the Earth's size is 1/100th of the size of the star. So 1/100th times 1/100th is, it's a very small quantity. So you have to be out of the atmosphere to have a chance to detect. But looking at this diagram, immediately see, we can spend a lot of money to build a new telescope in the space and to search for planets. And today we have at least maybe 5 different spacecraft looking for this effect. So what is behind this idea is the fact that we would like to find convenient planet for life development. And the basic question for this is a statement made by the Nobel Prize in Biology, Christian de Duve. Do we have to consider life as a cosmic imperative? What is the meaning of this sentence? Is if you have all the good conditions for the development of a chemistry of life, do we have automatically life emerging, or if it is something different? So this is a very fascinating question for the future that we have in front of us. And I'm sure Didier will discuss a little bit. And I will finish with a calculation. Maybe it's not the good place to do it here, but nevertheless I will do it. Apollo 11 went to the moon in 3 days. The light needs only 1 second to go. So let's imagine that you are finding an absolutely perfect planet for life development at, let's say, only 30 light years, something like this. 30 light years is small. It's one of our neighbor. really. And then we need 1 billion, the light will need 1 billion of seconds to go to this planet. So if you have the same spacecraft as Apollo 11, we need 1 billion times 3 days. Start to be long. And then you are very, very optimistic people. So you say, okay, Apollo 11, maybe we can accelerate. But no, if you want to accelerate from 11 kilometers per second to the close to the velocity of light, the amount of energy you need to accelerate is completely crazy. And after you have to decelerate. So the only statement we can do from this, if at some point the Earth starts to be inhabitable, in fact, we have no way to escape and to move, because sometimes people say, oh, it's nice to detect habitable planet in the universe because maybe humanity will has the possibility to emigrate at some point. No, it's not possible. We are linked to this planet, and we don't have plan B possibility. Thank you. I will just finish with one slide. This is a new telescope in construction with a diameter of 39 meters. I don't know, it's something like similar to this room. So the adventure continues.